Today I'm going to talk about fast radio bursts. It's a passion of mine in astronomy. As Truman alluded to, I have other passions these days as well, but today it'll be fast radio bursts. Most of the sponsors here on the slide are teams that are collecting data in the radio to detect or characterize fast radio bursts. The team that I'm most a part of, and I'll introduce those team members in a moment, is the center logo, the fast and fortunate for FRB follow-up. We call ourselves F to the fourth, and we chase after FRBs at other wavelengths, including radio, but not to detect them ourselves. I want to give a shout out to the Simons Foundation because I will be funded by them for this oceanography passion of mine. If you have not heard of the Pivot Fellowship, feel free to ask me about it, or you can read about it on the Simons web pages. But let's stick with fast radio bursts today. And as I said, we'll introduce the team. We're about 15 or so scientists across the world a little bit, primarily in the United States. Primarily young. The leadership, if you want to call us that, are myself and the three folks down here at the bottom, Regina Jorgensen at the Maria Mitchell Observatory. Who knows where the Maria Mitchell Observatory is? Where is it?
It's like Massachusetts.
Good. Not quite Cape Cod. Nantucket Island is correct. She is the director, astronomer, quite the gender, but the everything of the Maria Mitchell Observatory. But she runs an outstanding REU program. Those of you that have undergraduate students, consider it. And now a post-bac program. And this young woman at the center is one of our post-bacs working on fast radio bursts. I'm going to show results from two of the grad students, in particular from UC Santa Cruz that I highlight, and then the remainder of the team, and this undergraduate who's not at the MMO, but part of our extended group who's on the PhD market. If you're interested in an outstanding PhD student, give his application a read. Right. I'm going to begin with a movie that I did not create, but I think is quite illustrative. It is very illustrative in what the dispersion measure is. Lots of people in the room have been discussing DM all week. It's not dark matter, it's dispersion. And what you're seeing is a pulse of radiation from a fast radio burst, say, from a distant galaxy, now traveling through the cosmic web. And as it goes through the plasma, electromagnetism tells us that the longer wavelength light has a retarded velocity compared to the shorter wavelength light, and that's a process that we describe as dispersion. The more material you traverse through, the more that effect. And as I'll show in slides to come, that gives you the dispersion measure that we record in a radio telescope. And I'm going to skip the remainder of the movie, but it is pretty cool. So that's dispersion measure, DM. I'm going to say DM a lot. It's not dark matter, not at least for this hour. It's dispersion measure. This is a fast radio burst. This is an image, if you want to call it that, of a fast radio burst. This is on the x-axis. Let's see, I got to figure out how to do this little lasery thing. There we go. On the x-axis, we have time, the arrival time of the photons, of the radio photons at the telescope. The y-axis is the frequency of those photons. And so you're seeing the delay of the shorter, lower frequency, higher wavelength light as recorded in the telescope. And this sweep, often called waterfall, is the characteristic image of a radio pulse here at fast radio burst. But if you study pulsars, the signal looks very much the same. Here is the first radio burst published, no longer the first one detected and recorded on a radio telescope. It was published by Duncan Lorimer. It's often referred to as the Lorimer burst as a result, like another waterfall plot, the x-axis, arrival time of the photons, the y-axis, the frequency of the photons. The horizontal line is some RFI, probably from a satellite communicating who knows what on Earth. The arrival time this is straight and simple electromagnetism. The arrival time is retarded as nu to the -2. And the greater the amount of plasma you traverse through, here recorded as DM, the dispersion measure, the greater that retarded time. Therefore, the dispersion measure formally is the path integral of the electron density. If you do this within our Milky Way, then you can ignore the cosmological expansion. And that's, again, what we describe in pulsar data. If the source is at extragalactic distances, then you have one scale factor in the equation. And so what Duncan appreciated, and this was serendipitous, I'm told, he had modified the search software looking for pulses from sources in the Magellanic Clouds, I think the Large Magellanic Cloud in this case, and accidentally searched to a dispersion measure that is unphysical for the Large Magellanic Cloud, and this popped out. And so serendipitous in that sense. The dispersion measure that the sweep implies is 375, and as I'll show you in the next slide, that's just entirely inconsistent with what any of our understanding is of electrons between us and the Magellanic Clouds. Hence, they inferred that it was extragalactic, and that is now held up to be the case. Here's a model, or description of a model of electrons in the galactic interstellar medium. So using pulsars primarily, but not entirely, we have mapped out electrons in the Milky Way. These authors, Cortez and Lazio, quite a few years back now, put together that data to build a density distribution of those electrons. We refer to this as the warm ionized medium, the WIM. And this is an illustration of it as of the dispersion measure that we would view on the sky from Earth. And most of what you see, of course, is electrons, ionized gas within the galactic plane. That's along the center axis, x-axis, if you will. There we go. There's a supernova remnant to the right-hand side of the figure that's dominating the signal there. And then as you move away from the galactic plane, the signal goes down to about 10 in these funny units of parsecs per cubic centimeter. I did not, in this cartoon, or this model, or this figure, show the Magellanic Clouds, but they'd be a small signal. In addition to that, here's where the Lorimer burst was located on the sky, and the dispersion measure that they measured far exceeds anything from the galactic contribution, far exceeds anything we could expect to be considered associated with the Magellanic Cloud as well. And that was the argument that these were extragalactic. For the next 5 or so slides, I'm going to talk about additional signals that we measure from the fast radio burst. One of them may seem trivial, but it's very important to the science that we pursue, and that's the localization. So where on the sky it's located. The original burst from Duncan had a precision of about 10 arc minutes. That's large enough, of course, that we can't associate it with any individual source on the sky, at least not with any confidence. In fact, it took about 10 years for the first FRB to be well localized, precisely localized. Here, precise means about an arc second, or in this case, actually, milliarc seconds. They use the VLBI. And when doing so, this repeating FRB, that's another one of their characteristics, some do repeat. I won't say too much about that today, unless asked. But this repeating FRB was precisely localized to that little faint blue smudge or white smudge, which is a galaxy, a dwarf galaxy. And here's another example, not from the VLBI, but from the ASCAP telescope, which I'll say more about. And the black circle is the localization, again, subarc second, and clearly located or associated with this somewhat distant galaxy. So second signal is the localization. Most of what I'll describe will leverage precisely localized FRBs, but there are thousands now on the scale of arc minute to 10 arc minute localizations. Another signal which I will emphasize is the rotation measure. So as this electromagnetic pulse traverses through the plasma, if that plasma has a magnetic field within it, and if that magnetic field is oriented parallel to the line of sight, then it induces a rotation measure, a rotation of the polarization of the EM field, again as a function of frequency. That's what's being plotted here. This angle, psi, in the right-hand plot as a function of frequency. There's a small but measurable change in that angle as a function of frequency. That is the rotation measure. And it is sensitive to the path integral now of not just the electron density, but the electron density weighted by the magnetic field along the sight line, and 2 factors of the scale factor. So this is a second signal that can be measured. It is measured for most FRBs, or most pulsars, and gives us access to the magnetic field, or a measure of the magnetic field within the plasma. Another signal I won't say too much about today is what in transient literature might be called the light curve. In FRB literature, it tends to be called the scattering time. The signal may also be influenced by the foreground medium. If that medium has density fluctuations, it will broaden the observed pulse, and one can therefore infer aspects of the density of the gas using the scattering measure of the pulse. And that also has a frequency dependence. Here's an example of data where scattering is believed to be occurring, where you can see towards the, that's not the one I wanted, that's the one I want, towards the lower frequency range of the signal, that the width of the pulse is nearly 20 milliseconds, where at higher frequencies much more narrow. This frequency dependence is expected to be, or predicted to be, nu to the -4, and this example follows that quite well. If you do localize the signal to a galaxy, then one may learn, one may measure whatever property of the galaxies you wish. I will describe a little bit of that as we go here, but that you can call the secondary signal. And this is a lot of the work that our team does, is following up, associating the signal to an individual galaxy, and then following up that data, or following up by the galaxy at multiple wavelengths to infer its properties. So in one slide summary of the signals at our hand that enable the science that I'll now transition to in the remainder of the talk, a dispersion measure that by and large defines what a fast Fourier burst is, its location on the sky, ideally with a precise localization so we can associate to a galaxy, the rotation measure, which gains insight into the magnetic field, the scattering measure of the profile, which has implications for the density of gas that you traverse through, and then the redshift if associated to a host. It's kind of a whirlwind tour introduction to FRBs. Let me pause there for questions on the signals. Good enough? All right. We may continue. So, why did I get interested in FRBs, you may ask? What motivated me was this gentleman, Fukugira, Masataka Fudagita-san, and the paper that he wrote with Jim Peebles and Craig Hogan in the late 90s, which became referred to as the missing baryons problem on cosmic scales. What they pointed out, what they did was a relatively simple exercise, but had profound consequences. They compared the estimates of the baryon mass density in the local universe, which I'll walk through in a moment, with an estimate of the baryonic mass density from the early universe. In their day, the early universe measurement came strictly from Big Bang nucleosynthesis analysis. But shortly thereafter, the CMB was also a technique one could use to infer the mass density of baryons. The two agree remarkably well. It's one of the most impressive feats of cosmology, in my opinion. And so they had a number from the early universe of what the mass density is, and then went into our backyard and counted up what one could see. And so what one can see are in the colored wedges on the right-hand side of this figure. The orange and the blue are stellar mass density. So just count up how many galaxies, make an inference on the mass-to-light ratio, and you have a mass density in stars and galaxies. The red wedge is using 21 centimeter observations to infer the atomic mass density in galaxies primarily. Gray for molecular gas, that's from CO observations. And the black comes from X-ray observations of hot gas in the universe dominated by the intercluster medium. And what they pointed out, and maybe alarmed the community with, was that that set of wedges was nowhere near the total expected or predicted from the early universe measurements of the mass density in baryons. And this Pac-Man, as it were, quickly became known as the missing baryons problem. 50%, perhaps as much as even 80% of the matter today, normal matter today, could not be accounted for in a simple census of the nearby universe, despite the fact that it's right all around us. So that inspired myself and others to spend 20 years and countless observatories chasing this problem. I gave a WAG of about $50 million of U.S. operations alone on these facilities and more. It's a challenging problem. Has been an extremely challenging problem because most of the techniques that we have to identify diffuse and relatively warm gas are not very sensitive. And indeed, the dispersion measure, the fact that with fast radio bursts or any pulse of radiation of radio emission, we could gain access to all of the ionized material is really what led me into FRBs. So let me continue the story with fast radio bursts. We then set forth to probe the cosmic web with FRBs. And we have a clean prediction for what that signal should be from cosmology, from our knowledge of our expectation of the baryon mass density and our understanding of cosmology. Let me walk you through that a little bit. Here's somebody's output of the cosmic web. I don't recall who anymore. First, I'm going to choose terminology I prefer when describing the cosmic web. That includes two dominant components. One, the intergalactic medium, IGM. For me, that's the gas in between galaxies, as the name implies. So from both mildly overdense regions to effectively voids, if you will. And then the circumgalactic medium, again, diffuse-ish gas around galaxies, so the gas surrounding galaxies, CGM. Together, those make up the diffuse gas or the ionized gas of the cosmic web. As I said in words, now in equation form, we have, from first principles, a prediction for what the dispersion measure of the cosmic web will be. It's primarily a function of the mass density of the universe, which comes in here, omega baryon. It also is sensitive to what fraction of the universe is in a diffuse ionized form. We have good estimations of that, percent level estimations of that. So we have, once one adopts a cosmology, an analytic expression, numerically solved, to predict the average cosmic dispersion measure through the universe, okay, out to a given redshift, what I will call average DM cosmic. What we then needed was an experiment to go and test or search for the baryons using dispersion measures. The experiment that's driven this so far to date is called CRAFT. It's on the ASCAP telescope, or it's performed on the ASCAP telescope, here pictured in Western Australia. It's one of the pathfinders for the SKA. Keith Bannister is one of the leads of that project, pictured here. And unlike many other experiments, it not only detects FRBs, but it localizes them in one fell swoop because the experiment is a large interferometer with up to 36 dishes. Here was the first FRB localized with that system. You probably can't even see it in the back. There's a red dot at the center of the figure on the left. It's about 1/10 of an arcsecond localization region. Lands right in a galaxy. We have a fully, if needed or if desired, Bayesian process for associating any kind of localized source, but here FRBs with galaxies. This one's unambiguous, or it's confidently at 99.9 something percent associated with that galaxy. Straightforward enough to get a redshift, and now we had our first, from this facility, which then became many, FRB with a dispersion measure and a redshift. Then the question becomes, is this straightforward prediction from cosmology, given the baryon mass density, correct? This is now a plot of that average DM cosmic as a function of redshift, the equation you saw a few slides back. Again, that's a straightforward prediction, analytic prediction of our basic cosmological paradigm. This is a prediction, a model prediction, not as secure as the black solid line, for the dispersion around the mean. And we expect physically a dispersion about the mean because we have structure in the universe. So some FRB sightlines will go through more structure, and you'll wind up with a measured DM from the cosmic web that exceeds the average. Many sightlines will go through patches of the universe that are underdense, and you'll wind up with a DM that's below the black line. Today we don't know, we have not measured, let's say it that way, nor can we predict well from first principles that this band here, which is the 90% scatter. And in fact, that's, as I'll emphasize, some of the ongoing work. But this is a good estimate or guess at what it might be. Here then were the first 5 FRBs in color that passed our set of kind of gold standard selection criteria for the experiment. In gray, a few additional ones that did not pass those criteria but plotted for completeness. And with running for about a year on the experiment, we had enough FRBs to make at least the first comparison with prediction. And I think you should be convinced, and indeed this gentleman was convinced, that we had detected the baryons that were always expected to be there, but had been just too elusive for all other experimental efforts. So great. Yes?
Why there is no error bar on
Can you use your seat mic?
Oh, use your seat mic.
Just push it in.
And a green light will come on.
And there you go.
Okay. Why there are no error bars on the y-axis?
Great questions. And indeed, this one, the analysis was done, and actually I'll go into it in more depth in the next couple slides, with a full forward model of not only the cosmic contribution, but the contribution from the host galaxy and also the Milky Way. If I were to include uncertainties on those, they'd be tens of units at a minimum.
Okay.
Yeah. But
Huge error bars. That's why you're not plotting.
I'm not plotting because that's not how the analysis was done. This was illustrative.
Okay.
But it's a good question. Yeah. Yeah. Those factors do contribute and have to be considered in the modeling. That's right. Other questions on DM Cosmic? So let me describe a bit more of the forward modeling. Here is where the data stands today. I think maybe module a couple of data points. Now I'm starting to introduce those additional terms. On the y-axis is now the contribution of all the extragalactic terms, which here is just the cosmic web and the host galaxy. From the data, we estimate that from the observed quantity, which is very well measured, and subtract off the Milky Way. So that provides all the extragalactic signal. From the model, we have both a contribution from the cosmic web and a model for the host galaxy, and that's included in the black line. The next slide will show you an estimation of the uncertainties in the model. This model, which includes a host contribution of about 200 units per of DM units, is a good description of the data, at least for these 16 data points. And as I said, as I've emphasized, the scatter about the average is both expected and in line with at least our current expectations for structure in the cosmic web and structure within the host galaxy. To do this really well, and now I'm getting into the guts of the analysis, one has to not only account for various contributions to the dispersion measure, here at both the host and the cosmic web, but also account for the fact that we have a finite telescope with a finite sensitivity. So that includes modeling of the energetics of the FRBs and a full accounting for the beam of the experiment and the size of the telescope used. So what's now plotted, again, what's plotted is similar to the previous slide: redshift on the x-axis, extragalactic contribution, so cosmic web plus host galaxy. On the y-axis, the data are the dots and the blue star, which was our most recent measurement. And now now you can see explicitly the uncertainties, which are the measurement uncertainties are irrelevant. There's no uncertainty there. The model uncertainties are significant, and I shouldn't say uncertainties. The model have distributions for the host galaxy and the cosmic web. Those are included here, and enable analyses on the McCoy relation, which is the dispersion as a function of redshift, and as you'll see in the next few slides, allow us to place constraints on the Hubble's constant and eventually work in progress scatter in the cosmic web, which relates to galaxy formation scenarios. Let me pause there on this figure. Question? Yes?
You lost me on this figure. I'm sorry.
Yeah.
What is the color showing here?
The colors, so the data, which are redshift versus extragalactic dispersion measure, have been modeled with the variety of components on the right-hand side, mainly energetics of the FRB and our understanding of the universe. The shaded region then is from the model, the predictions, the PDF of where FRB should land in this space.
I see.
Yes, I should have. And so the parameter, the model parameters that give the best match of the data is being shown here. There are, of course, uncertainties in the model parameters that give you a range of PDFs. Yep.
So the sort of paradigm you're using here is that there's a roughly homogeneous universe through which these things are passing, and it's sort of random whether you happen to pass through the structure that gives you the dispersion measure, but could you use information about where they are on the sky and like sort of what structures they're sitting in?
That's right. Can one cross-correlate the known position with known structures in the foreground? Yes. Stay tuned for a few more slides. But in the model shown here, that has not been included, that additional information. Yeah, great question. Other questions on this? Okay. So we set forth with the current data to both make a forecast and a measurement of Hubble's constant. So the average DM cosmic, I should have emphasized it when it went by. I can go back quickly. The average DM cosmic also includes Hubble's constant in our evaluation. And it also comes in through the critical density. Now, we use as a prior measurements from the CMB and Big Bang nucleosynthesis, the combination omega B H squared. So that's very well measured. That's a prior in the analysis. But we still have a lingering dependency on H naught. And hence there's power. I didn't include in the slide deck, but if I were to shift H naught in the model, these curves, actually increasing H naught would shift these curves down. And decreasing H naught will shift them up. And actually most of the constraining power comes from what we call this kind of edge in the PDF. I cannot, in most of the power, as you can probably then intuit, I cannot reduce H naught too far or I will exceed the measurements. Okay, or I won't allow the low values that we actually observe. And you can see that as well. There's a sharp edge at low H naught, low Hubble parameters allowed for by the data, and then a long asymmetric tail to large values. This is not precision cosmology. Of order 30% errors on H naught from 16 or so FRBs. Here's a forecast what one could achieve, ignoring not ignoring all systematics, but ignoring one that we've only recently uncovered. So I'll say a word about that. And one could achieve with 100 FRBs something approaching 5% uncertainty, which does get interesting for those of you that are placing bets on the current H naught tension. Turns out there's an additional degeneracy, if you will, between H naught and this parameter that will make H naught more challenging. And I think the focus for the next year or two is going to be instead on what I'm calling F. F is for feedback, although it's inversely proportional to feedback. I've added additional equations here. The main one is, keep it in that button. The main one is here. This is a PDF for the dispersion about the mean of the cosmic web DM. All right, so I cartooned that as the shaded region a few slides back. Here's an analytic expression that was fit to simulations. That's a pretty good description of the simulations. For that PDF, delta is just the value over the mean. Okay, so this is a PDF of the dispersion about the mean. And it's parameterized by a few numbers, but the one that we allow to vary is this capital F. Okay, and we're going to call that the feedback parameter if you want. And that's what our scientific focus is on today. And what it relates to is galaxy formation feedback to 0th order. That is how homogeneous is the universe. If I make F very large, the universe is very inhomogeneous, so that I have not redistributed the baryons outside of the potential wells that are galaxies. If I were to make F 0, I'd have a completely homogeneous universe, which is akin to saying galaxies have reshuffled the baryons in such a way that they don't follow the dark matter whatsoever. Okay. So F becomes the focus. This is just a cartoon of some of what I just said. If I increase F, then I make a very inhomogeneous universe. I've got a wide distribution of dispersion measures about the mean. If I make F very small, that's the very thin line here, then all of my dispersion measures would be right about the mean. Here's a forecast for F from 100 FRBs, which we expect to be at probably next year. The blue is if we adopt a pretty agnostic prior on H0, on the Hubble constant. The shaded curves, or the dash curves, are for the currently best low. I think what is low is from CMB and highest from supernovae. I think I have that right. To the extent that we can nail down H0, then we will have yet more precise measures of F. Let me, since I know there are a lot of cosmological simulators in the room, all of you can calculate F today from your favorite simulation. Please do. It's not hard. Probably would take you, 1 hour or maybe less to just collapse your box and measure F. We will have a 20% measurement within a year, I would predict. Today we have something that's not that's useful, and it will be published early next year. So if you are running large box simulations, please place your bets now and expect a 20% measurement within the next year. Let me go from the larger scales. Oh, please.
Is there not a... I got my mic on, but I'm shouting, so it's hard to tell. Is there not a degeneracy between F and large-scale power, or power at the filament scale?
Is there not a degeneracy between F? It
Right,
is driven by...
F is about how baryons are spread out, but baryons also follow dark matter.
Correct.
And something like sigma 8 is a measurement of how spread out dark matter is. So are these things not related?
I think what you're saying is if you would need to have a suite of sigma 8 simulations, or there will be a degeneracy between the F that will be measured in your box, between the effects of galaxy formation versus sigma 8. I think that's right.
Yes.
I agree with that.
Okay.
Yeah.
So you need to measure. Simulators need to
specify what
F
sigma 8 they're using
for their model and
and be aware that sigma 8 should have a non-negligible effect. I agree with that. Mm-hmm. Good point. Yes, go ahead.
You also had a redshift to the minus 0.5 dependence.
Ah, yes.
Are you certain about that? Or?
No. No. It's sensible in it's intuitive in the sense that as you have an FRB at a larger distance, the Poisson variations of structure formation are such that you go through more structure, right? So then sigma should drop in that respect. And I'm sure that's how it scales. Well, I'm sure that's why there's a dependence. The analytic formulations what allows us to do the modeling we do. Those that are running simulations don't need to. You can tell me what your z exponent is. There is one publication. I think someone used Illustris, and in their model it was roughly z to the half above redshift. I think 0.4 or so, but steeper at lower redshifts. If I remember. Okay, galactic scales. So FRBs, I've hopefully impressed upon you, have a new avenue to make constraints. Ultimately, I think on H0, although that's going to take some more time than we had envisioned, maybe in the shorter term cosmic structure. Now let's go down to galactic scales. I'm showing here a not so well localized, but well localized enough FRB. I'm trying to remember. I think from the Westerbrock telescope. Not too important. That occurred next to, at least as viewed on the sky, M33, I think that is, and kind of announced to the community, these sight lines are going to occasionally go near bright foreground galaxies. Much the same game that I've played for decades, I suppose, with quasars. And we're starting to do this experiment as well. So what does that gain you? We've had quasars and been doing that experiment, as I say, for decades. What FRBs gain you? Well, they gain you new insights because of the difference in the signals. In principle, and I'll emphasize this towards the finish, one can gain new insights into the ionized gas profile around galaxies, what we call the CGM. It's been very challenging to do, especially for all of the gas, as we can use NE here. That's in play, but I won't have results on that today. I'll show you one result from one galaxy on using these signals. The scattering, which I mentioned, that's the broadening of the profile due to propagation through a turbulent and dense medium. And then the rotation measure, which gives us some insight into the magnetic field. And beware, especially the latter, rotation measure is an integral quantity. So we have to keep in mind other things can contribute. I'll say that again in a moment. Here's the galaxy in question, which we've now published a couple years back. The FRB is the red ellipsoids in the lower right, associated with that galaxy at a redshift of nearly redshift a half. And coincidentally, there's a foreground galaxy, physically unassociated, and only about 20 kiloparsecs separation on the sky at the galaxy's redshift. The broadening, there's no measured broadening in the FRB signal. So there's an upper limit of 40 microseconds. And could have been, in some telescopes or some signals are bright enough to get down to nanosecond timing. So this can be very powerful, but even 40 microseconds, you'll see has value. And a rotation measure of only 11 radians per meter squared in those funny units, which is also a small number, I assure you, for rotation measures. So both in terms of RM and T, the signals were weak. This let us place tight constraints on the density fluctuations in the gas on this scale of 20 kiloparsecs away from a galaxy, what we typically refer to as the CGM, as well as the magnetic field in that galaxy. And that's what's depicted here. The hashed regions are regions that have been ruled out of this parameter space of the average cool density in the gas and the magnetic field oriented parallel to the sight line. The densities higher than about 1/10 particle per cubic centimeter ruled out from the scattering measurement, and the rotation measure rules out the diagonal region depicted across the figure. The yellow was some previous estimate for the magnetic field strength in the halos of galaxies. This one measurement's inconsistent with that mean that also came from rotation measures, but they're from quasars. So as we build up a sample of FRBs, by accident, by coincidence, we'll have foreground galaxies associated with some of them or near some of them, and be able to repeat this experiment on first handfuls and eventually tens, if not hundreds of galaxies. Yeah.
Why was that the cool number density? Why not just all electrons?
That only because I stole it from the paper without removing the cool. But we had two models, a cool model in the paper. But yes, warm would be just. The gas could be any temperature, and the constraint would hold. What else, in terms of gas around galaxies, can we do? M31, I am predicting. I'm not part of this, but will be well resolved within the next year or two, maybe 3. The CHIME experiment, which is recording a few FRBs a day in the northern sky, covers M31 in spades. This is the signal from a model I produced, a guess at what the dispersion measure from M31's halo might look like. Very easily detected in a differential experiment that CHIME can do. Similarly, it's possible with a southern experiment, which doesn't exist, that produces but could exist, say SKA. One could do a similar thing for the Magellanic Cloud's weaker signal, more challenging, but probably not impossible. So stay tuned for that. Back to John's question about cross-correlating foreground structures. So we've begun this effort. The overall project's called Flim Flam. It's a KG Lee production. He'll show up in the next slide. But our first publication was led by Sunil Simha here, where we had an FRB occur in the Sloan footprint, and we made use of the Sloan Digital Sky Survey, the knowledge of positions of galaxies on the sky and their masses, to predict the density of foreground structures and put together a holistic picture of the DM. It worked quite well. But what we're headed for is doing this for 30-ish fields, not just one. There's KG pictured. Hopefully I've convinced you we've detected the missing baryons. Now the next phase is to figure out where they're located. And these are forecasts for constraints on, maybe I won't read through all of them, but constraints on a measure of how much of the material, what fraction, let me say it this way, what fraction of the baryons are located within the CGM as opposed to the IGM, in simple terms. And with 30 FRBs, we think we can get that number to of order 10%. Maybe that's optimistic, maybe it's 20%. We're collecting the data now. I expect we won't publish it next year, but probably the year after. So we'll have a publication soon, but not the full sample. And then eventually, I'll save that for yet other future things. So we're headed there, but stay tuned for results. Let me spend 10 minutes on this last topic or less, maybe 7 minutes. Please.
Just a quick question of how you differentiate between the CGM and the IGM. What actually is the difference in that case?
Here defined in this model, I believe it was 1 times the virial radius, but we sometimes account it to allow it to be 2 times the virial radius. So we scale with the virial radius, short answer. Okay. That choice is arbitrary in my mind. Not entirely arbitrary, but I wouldn't defend 1 versus 2 with great emphasis. But here I think it was 1.
Thank you.
Yep. All right. Last bit on using FRBs as probes of the universe. Here now we're going to leverage the signal to infer aspects of the magnetic field in the host galaxies. So I've largely, not entirely ignored the hosts, but now the science is on the galaxies hosting the event themselves. Here's an example that occurred, or at least coincident with the spiral arm. As you'll see, we've now measured of order 10 FRBs, localized 10 FRBs, and measured the rotation measures. There are many more recorded. So this is the first of what will be an expanding field. This is work led by Alexandra Mannings at UC Santa Cruz. And let me show some of her key figures. This is now posted in archive. Here's one FRB just of part of the sample. Here's the sample of about 10, mainly star-forming galaxies, mainly in the star-forming main sequence, with a range of masses, pretty large range of star masses. And I'm not going to show you a figure, but the offsets, they're typically offset from the nucleus. The localizations tend to trace the light or the mass, as we assume from the light. Here are the rotation measures on the y-axis plotted against the redshift of the FRBs. There's no correlation. We did not expect a correlation, unlike the dispersion measure, which shows a tight correlation with redshift. We see none. This is as expected. We do not expect a significant signal from the intergalactic medium, and nor is one seen here. So the absence of correlation implies that the cosmic contribution to the rotation measure is small. And therefore, we can invert what we observe, the RM FRB we observe, subtract off an estimate of the Milky Way signal, which is derived from quasars, by and large, to infer the RM of the host. That's plotted here against two of the properties, an estimate of the dispersion measure of the host and the offset from the galaxy, which I said kind of traces the light to 0th order. This positive correlation, that negative correlation is what one would predict if the magnetic field strength increases towards the center of the galaxy, or and also if the rotation measure is occurring within the host galaxy itself. So evidence at the 98% maybe confidence level that this rotation measure does know about the host galaxy. We may then, what was that question? Sorry. We may then make a crude estimate of the magnetic field along the silent line of sight, relating the rotation measure dispersion measure. That's what's plotted here. The Milky Way, the local value for the magnetic field is of order 5 microgauss. That's the dotted line. The dots are this approximate estimation for the parallel magnetic field in the sample of 10 FRBs. You'll note one that lies way out amongst the population. That's the first actually FRB localized. It's got a very large RM, and it's believed that's been highly skewed by the local environment. That's part of the nature of the experiment, is the local environment can matter, but clearly for this ensemble, the majority are low magnetic field strengths, even lower than the value estimated for the local Milky Way, but consistent given that we expect some field reversals. So this science has started as well. I bet there are over 100 FRBs. I know there are over 100 FRBs with rotation measures recorded now, not localized so that you can do all the analysis you just saw, but probably maybe 20 or 30 and rising. So I'll conclude with a handful of slides on where the field is headed. It's promising in terms of data. This is showing you the number of FRBs published as a function of year. At least blue is published. I think red is just what I know about. For all FRBs is blue, localized to about an arcsecond in red. You can see this exponential growth in both of those measures. The blue is driven by the CHIME survey, which is detecting several FRBs a day. That plateau is only because they stopped publishing, or they only published their first data release in 2019. I know they have, I believe, 3,000 FRBs today and counting. So that's continued to grow at that pace. And the red curve has been driven by this ASCAP, or the Kraft experiment on ASCAP. And that's led to exponential growth for the last few years, and the field is poised to have yet another leap. Kraft is upgrading so that its rate will increase tenfold on the ASCAP telescope. That's a computational advance, or new GPUs to increase the processing power and detect more FRBs. CHIME is adding outriggers. So CHIME itself is located at the blue star, and they're adding a handful of outriggers to the experiment so that they can localize the FRBs they detect to milli-arcsecond precisions. That'll lead to a handful of localized FRBs per day, as opposed to our current rate of about 10 to 10s per year. DSA has turned on, and I'm told they will have a publication at the AAS, so I'm expecting tens of new sources from them as well, also driving the field. And last, just a few kind of science areas I know about. I thought I'd highlight, even because they're not published yet. This is work from the CHIME experiment that I'm aware of, a paper that's been shared with me. This is going to place a very tight upper limit, tight upper limits on the gas in our own Milky Way. So those of you that may be considering the density distribution of gas around our galaxy, stay tuned for that. That's using the CHIME experiment. We've now pushed out, you've seen it in a couple of the slides, but let me emphasize it. We've now pushed out to redshift 1 with FRBs. We've kind of stalled at redshift 1/2 for the last 2 years. Despite a handful of high dispersion measure sources being known, they had not, either we couldn't get a redshift for them or they had not worked out to be at redshift 1. This one did. So we now know we're going to detect these well beyond. This actually was a very bright burst in terms of signal noise, so easily detected at redshift 1. Clearly, we're going to push well beyond that. There are host population studies that have been published, but I think the next round are going to really start to be able to look at correlations between properties of the galaxies and probably properties of the FRBs as well. So if you're interested in using a host as progenitors, that data is coming in spades. And I'm excited, I don't do any of this analysis, but I'm excited by the prospects of using lensing experiments with FRBs. If that interests you, check out this nice paper by Liam Connor. And he's described the parameter regime for the lens masses that one can gain access to both planned FRBs and kind of the next generation FRB experiments. And I'm going to stop there. The probable column here, if you want to read the text after I stop, I'm confident will happen. The optimistic, I'm hopeful will happen, and the overly optimistic are things I'm not so sure will ever happen. But we will be leveraging these for the next 5, or probably for the history of astronomy, hopefully. But within the next handful of years, this I expect to happen. That might happen. I don't know about that one. Thank you.
Okay, any more questions for X before we go have a glass of wine?
Mary in the back.
Yeah, thanks, X. So I wanted to know how you deal with the Milky Way clumpiness in the CGM, or do you just assume it averages out? Especially with something like the Magellanic system flying through.
Yes. So the short answer is it's been treated as an homogeneous, so no clumpiness other than the warm ionized medium that I showed you in whatever slide 5 or 6. So no M31 and the Magellan clouds have been ignored to date. I don't think any FRBs have landed close enough for that to have mattered, at least in the analyses you saw. If there's clumpiness on smaller scales, like if there's an asymmetry to the distribution of gas in the Milky Way, may well be. That's not been included in any of the modeling. I'm pretty optimistic that one of the last slides you saw, that the data will be sufficient to explore that. CHIME is, the full northern sky, at least on that angle on the sky, one should be able to test for anisotropies. Mm-hmm.
The ISM turbulence measures, how do you disentangle the turbulence in the nebula itself, like close to the source and actual galaxy?
That's a good question, and I'm going to steal this cartoon. So for the scattering measurement, the broadening of the signal due to turbulent dense gas along the line of sight, conveniently, in part, the signal is maximal at half the distance. It's similar to it's the same, actually, at least mathematics, of gravitational lensing. So a turbulent medium very close to the source or turbulent medium very close to us is way downweighted. That's not to say it's negligible or zero, but it's highly downweighted. In the results I presented to you, we didn't detect any scattering, so in that case it was easy enough to, we've provided an upper limit. If there were a contribution locally, it'd be part of that upper limit. When one then goes to a variety of observed scattering measures, you're going to have to include that in the modeling, absolutely. Yeah.
Of course, timescales also can play a role. Like the nebula definitely has shorter timescales and a turbulent eddy turnover time than the ISM does. So, but it's tricky to disentangle only based on that. So this is a good kind of additional test for that.
Nice.
Thanks.
My question, just sort of, you were optimistic that in 5 years we'd have this would probe the turbulence of the ISM somehow, and I didn't follow exactly where that came from.
And it's, we scattering measure for sure. I know we're going to place tight upper limits. It's going to be a model, and it'll have to be a model-based inference of the actual value that accounts for a gas in the ISM of the host and in our own Milky Way, that we can model pretty well, given our knowledge of the electron density distribution in the Milky Way. In the most optimistic scenario, we have FRBs occurring far out from, I can already show you an example of FRBs occurring far out from the interstellar medium. We can reduce that term. But the very local term, I think, is always going to be a nuisance factor. Yeah.
Really quickly, before we go to your question, can you put just because it builds on John's exactly, can you put the current limits in like kilometers per second? Like what are the limits in terms of turbulent velocities?
And not standing here. Yes, I think, let's discuss later.
Great. Okay, sure.
Perhaps a naive question, but do you get the same inference or the same dispersion measurements each time for a repeating FRB? Or could that tell you about conditions kind of very close to the source? Or,
Some of the repeating FRBs have dispersion measures that wander. I'll back up and let me give a more complete answer. Only about 10-ish% of FRBs are known to repeat. It's conceivable all of them do, but as far as what's been measured, only of order 10%. So of those where that experiment can be performed, some of them do have dispersion measures that wander. Someone may correct me. I think most of the wanderings of order 0.1 DM units or less, so are relevant to anything I've said. I think some might exceed that and even be unit level wandering. And yes, presumably those folks that are, it's got implications for both perhaps what's generating the signal itself, but maybe more the environment that it's embedded within, That's a good question. The rotation measures can wander considerably, more than what I just described, and have.